The properties of logarithms tell us that the logarithm of a product is the sum of the logarithms, the logarithm of a quotient is the difference of the logarithms, and the logarithm of a base raised to the power is the product of that power with the logarithm of the base. Here's some examples. We want to expand an expression that looks like this, log base 3 of 4 times x. I see that this is multiplication right here, 4 times x, so I apply property 1 for logarithms to write this as log base 3 of 4 plus log base 3 of x. So I say the logarithm of this product is the sum of the logarithms. And it's true for any value of x that I want to substitute in here that this is defined for. If I simplify this expression and this expression, I'll get exactly the same number. Let's look at our next problem, log base 6 of 5 over x. This is a quotient, so I'm going to use my second property of logarithms to say log base 6 of 5 minus log base 6 of x. And property 2 for logarithms says that the logarithm of a quotient is the difference of the logarithms. So here's property 1, log of a product is the sum of the logs. Property 2, the log of a quotient is the difference of the logs. Here's another problem. Log base 9 of cube root z. I'll rewrite this as log base 9 of z to the 1/3. Then I use my third property of logarithms to write this as 1/3 log base 9 of z. So exponents become coefficients with property 3 for logarithms. The logarithm of this base raised to this exponent is the product of that exponent with the logarithm of the base. So there's property 3 used to simplify that expression. Next I have this. I'm going to rewrite this as log base 10 of x squared y divided by z to the 1/2. Now, as I expand this, I'm going to get log base 10 of x squared plus log base 10 of y subtract log base 10 of z to the 1/2. So here this is multiplication, so the logarithm of that product is the sum of the logarithms. It's division with this, so I have the logarithm, that becomes the difference of the logarithms. The only thing I have left to do is to take these exponents and write them out in front. I'll do that and end up with 2 log base 10 of x plus log base 10 of y minus 1/2 log base 10 of z. So there I've expanded this expression as much as possible using my properties of logarithms. You see each of my exponents becomes a coefficient. Where I had multiplication, it turns into addition, and where I had a quotient, it turns into subtraction. Now let's go the other way and take one that's in expanded form and contract it back to a single logarithm. Write as a single logarithm, log base b of x plus log base b of z. I see I have the sum of 2 logs here with the same base, so that's going to be the logarithm to that base of just that product. So the sum of these logs ends up to be the log of that product. Now as I move down to problem 6, you see I have a more complicated expression. What I'm going to do is rewrite this by first taking the exponents or the coefficients back up as exponents. So I'll write this as log base 2 of x to the 3rd when this coefficient goes back to that exponent plus log base 2 of y to the 1/2 when that coefficient goes back to an exponent. And then here, I'm going to even take this one with me. This is just my preference for doing this problem. Not everybody likes to do it this way, but I do. So I can think of this subtraction sign as a coefficient of -1. I'll take that back to that exponent on z. Now, it's all addition right here with logarithm of the same base, so I'm going to use property 1 for logarithms to write this as log base 2 of x cubed times y to the 1/2 times z to the -1. And then if I want to simplify this further and write my exponent of 1/2 as a square root and my exponent of -1 as a reciprocal, this will become logarithm base 2 of x cubed square root y all divided by z. So notice my exponent of 1/2, I write it as square root y. My exponent of -1, I make the reciprocal of the base, so it's 1 over z. And here I have a single logarithm that's equal to this original, more complicated expression. So I've contracted that expression down to a single expression here using my properties of logarithms. Let's look at one last problem. Here we have a logarithmic equation that we want to solve. Log base 3 of x plus log base 3 of x minus 2 is equal to 1. Well, here I have the sum of two logarithms, so I'm going to write that as the logarithm of a product. So log base 3 of x times x minus 2 is equal to 1. So I see, using my properties of logarithms, I can write this as a single logarithm. Now, this is just a single logarithm statement, so I can write it in exponential form as 3 to the 1 is equal to this. So I'll change this from logarithmic form to exponential form using the definition for logarithms. 3 to the 1 is equal to x times x minus 2. So here I've used my properties of logarithms right here to contract this down to one single logarithm. Then I use my definition for logarithms to change this from a logarithmic form into exponential form. And look, all I have left is a nice quadratic equation. Should be pretty simple to solve. Let's just go through the steps. 3 is equal to x squared minus 2x. When I multiply this out here, I'll put this in standard form by adding -3 to both sides. X squared minus 2x minus 3 is equal to 0. I want to factor that expression on the right. We'll factor into the product of two binomials. So x minus 3 and x plus 1. Is that right? Yep, got that right. Set those two factors equal to 0. X minus 3 is equal to 0. Or x plus 1 is equal to 0. Solve this, I have x is equal to 3. Solve the other one, and I have x is equal to -1. Now, I need to check both of these solutions because my original equation involved logarithms. Even though I ended up solving an exponential equation right here, it came from an equation that involved logarithms. And remember, the domain for any logarithmic function has to be a positive number. So when I look at this solution, x equal -1, if I substitute it back in here, I have log base 3 of -1. That's impossible. There is no expression like that. So this solution, x equal -1, is extraneous. If I go to this solution, x equal 3, and substitute it in either place, I get a defined expression, and x equal 3 will make this a true statement. So logarithmic equations there, an example of one that we solved using the properties of logarithms, the definition of logarithms, and we have to go back and check both of our solutions to make sure one of them isn't extraneous.